Okay, so hi, hello to see you all again. It's me again to talk about the rest part of our lab. Okay, including the HiC part and TED part. All this information we haven't touched, but will be required in the homework. Okay, let me share the screen first, and then we can start talking about some of the announcement. Okay, so first of all, I hope you guys are enjoying the first half of the homework and also the first half of the lab. If you haven't started yet, try to do it quickly because for some sections, it might take a longer time than the previous homeworks. But if you stick onto the instructions we provided, especially the ones we provided in this slides, you would probably be fine. But you just want to start it earlier. Okay. Now, the lab schedule. Last time, there's another student asking after our lab, whether are we going to have, classes this week, and I told them, we would. I was wrong. Okay, sorry. I didn't realize we have this spring break and this wellness day this week. So the new schedule, the updated one would be. So now what you are watching is the pre-recorded lab that would cover the materials that were originally supposed to be covered on Tuesday. So we are moving that into a pre-recording session. But for the Thursday, Friday, and Saturday office hours and QA sessions would remain the same. So please drop by if you have any questions. Also, as always, if you have any additional questions, you don't have to you don't have to stick with this schedule. You can just select the other students from the group, and trying to see if we can collectively get a good answer. Okay. Okay. Now, since last time we talked about the lab and the homework, there has been a lot of different questions, emerging from the homework. It in part because now this part 1, part 2 are relatively new questions that we haven't had this HiC and BI sequencing questions before. So we are kind of developing it from scratch and trying to adapt the version to the Canon server, and that is leading to tremendous version control conflicts. Okay, so I apologize for that. If you have any, if you see anything strange or anything you cannot explain, try to reach out to us. Okay, but hopefully most of the frequently asked questions are I try to summarize them here. Okay, so first is the environment related issues. The version conflicts. First of all, because we are providing the environments and data in the shared folder, like I said in the last step, try to copy them to your local folder first. Just trying to avoid, messing up with others, with other students. Technically speaking, you shouldn't be able to override anything over there, but just in case, try copy it first and to do your local folder. Another reason to do this is because this shared folder is on one disk, and if different nodes, different users are trying to access the same file, you might result in a slower response. So you don't want to be delayed, get delayed just because of that. Okay. Second, we recommend all of you to use the interactive nodes instead of the non-interactive nodes, and also, of course, do not use the login node. The reason we want you to use this interactive nodes is because for Canon, the setup for Canon, the configuration is that interactive nodes and non-interactive nodes, they have different conda environments. They have different ways to initiate the condas. This is in part related to the Slurm, the srun or sallocate commands. But to avoid those issues, just try to stick with interactive nodes. If you want to use non-interactive nodes, you might want to reinitiate your conda every time, and probably the conda initiate might not work. So you might also directly source the environment directly using the source activate. And then put the conda environment location, the path there. Yeah, so if you still see some problems, you can also try to add this line to source the directly the conda installation initiation script. Just try to override the module loading just to see if that could help. Okay, but again, we do not recommend you to use non-interactive nodes here. Not because in the daily research that's not a good practice. That is a good practice, but it's for this homework specifically. We have a lot of version conflicts, so try not to to do too fancy about that. Okay, and thirdly is that remember now we actually have 3 versions of your environments. One for part 1. No, so we have 2 different genomes. One for part 1, one for part 2, and the others. We have 2 environments. One is called Conda env 37. That is the Python 37 version, and there's a specific one called Homer environment, and that would only be needed for part 2.3. Okay, so you might need to switch between these 2 environments if you want to switch between different questions. Okay, just keep that in mind. Now, another question that is, we got a lot of feedbacks is the question part 1.1.2, where we asked the grad student to build the genome, genome indexes. Okay, so first of all, this genome building thing can take some time. So if you see your job has been running for half an hour and you still see that it's still running, there's no response, don't panic yet. It's supposed to take like at least say 40 minutes, 1 hour, and it can take, depending on the nodes, can take up to 3 to 4 hours. Okay, so just plan that accordingly. When you reserve a node, reserve a longer time. Not like 7 days, of course, but it's just try to put something like 4 hours or 6 hours, just to be safe. Also, second, after you build the genome, you would see a lot of printings, during the genome index building and the genome preparation. But we don't want you to copy all the logs into the homework. Now try to focus on these 2 files. One is the SE report, one is the duplication report, and reading those tags would give you all the information you need to fill in the summary table that we put originally in the slide. Okay, what we need in the homework would just be a table like this with all the critical, the key informations, including total race, alignment, unalignment, how many CPGs do we have, how much how much of the CPGs are methylated. Okay. Also, the third point is a kind of a typo we put originally in the homework. We say we want you to copy them. We copy the files to the local machine, but instead we mean we want you to copy them to your local machine on Canon. So you want to copy it to your local home folder instead of your personal laptop. Specifically because now for this question, the genome building can be very, very heavy, and you do not want to host or to run this kind of things on your personal laptop. And also on your personal laptop, you wouldn't get access to the environment that we provided on Canon because you do not, you do not have all this, module load and everything. So a lot of packages would be missing if you want to do things, on the personal laptop. Again, trying not to do that, not because this is not a good practice, but because specifically for the version control, trying to stick with the the environment we provided. Okay, so that's the announcement for part 1.1.2. For part 2.1, for the run HASI, we received the most errors and issues. So make sure you start this question as early as possible, just to avoid getting confused or getting delayed on this specific question. So this run HASI software, as we also mentioned last time, is not very well developed or maintained. It's not a blame. It's just when we are trying to use the package or software developed by other people, by third party, we should always be cautious about how to use them. So here, after a large amount of testing, we picked we picked one feasible solution, and we're trying to summarize it as the tree structure. So trying to set up your working directory exactly as what we provided in the previous slide. double check, triple check the tree structure to see if they look exactly the same, because any difference might lead to an error, and the error would be very confusing. Saying something, it's not going to tell you something is missing, something they cannot find. It will tell you, they cannot align the data, but actually what that error message is saying is they cannot find the file. So for example, one very frequent issue is that when you copy your HiC subregs folder, make sure that the FASTQ files are under the under the desired path instead of under a subfolder. So just try to double check that. Secondly, some of the HiC run HiC jobs, they might fail, but you wouldn't see directly from the terminal. So when you type in the run HiC commands, you will see a lot of logs, and then in the end they say it's finished. But sometimes, even though it's finished, it doesn't mean it's finished successfully. So you might want to check the log for each step to make sure make sure in the log it's saying each step is successfully completed. So if you see an error message in the log, you have an error message for this step, so do not proceed yet. Yeah. Thirdly, and this is another very annoying thing you need to keep in mind, is that if you made some mistake when you're testing or debugging this run HiC, and then it might also be the case that you prepared everything, you got everything correct, but your model still failed. That is probably because you failed before, and the run HiC is remembering all these failures. So they consider your last step has been finished, so it will skip rerunning that step. So even though now your setup is correct, your entire runtime configuration is correct, but the run HiC is not going to rerun and overwrite it. So you'll still see error messages in the following logs. So again, try to, if you see that, try to clean up the working directory to remove those, folders ending with HG38. Remember to add this hyphen, because we also have this one folder called exactly HG38, which is our index genome. You do not want to remove that. You only want to remove those intermediate files. And also specifically remove those complete files, because that, for some of the run HiC commands, they are using this completed file as the indicator that whether the previous job has completed or not. So that's it. Also keep that in mind in your future research. That's not the best practice. Yeah, so that's all we have. Kind of a brief summary of what are the questions we got from the QA session and from the office hour. So hopefully that is that can solve most of the problems. And and now let's move on. So the first part we are going to cover today is the cooler. It's the cooler Pikachu and HiGlass with all fancy names. So just to break it down, the cooler is a package that designed a data type specifically for genomic interactions. Okay, it's called cooler because it's using this COO sparse matrix data, and they're trying to make their name cooler by calling it cooler. The Pikachu thing is I find this very interesting. It's trying to find the peaks from your genomic information. So it's actually, I guess that might means catching the peaks. So pig catch. So it's called Pikachu. The HiGlass is a tool that can be used to visualize your HiC interactions. You have this online portal that can be used for some of the public data. But if you want to customize your own data, you need to develop your own HiGlass. Not really develop, but you need to use you need to call and import this HiGlass locally. So what is cool files? Or what is so cool about it? Okay. So we have already played around with these so-called bad files, where you have these locations of your genomic specific genomic region, and you can have a value. In our previous case, in our previous example, this value is gene expression level. Okay, and now imagine if we are now trying to move on to looking at the genomic interactions, we would have two locations. location 1 and location 2. And you will have a value, whether that's, for example, whether that's interaction, whether that is interacting or not, or how frequently they would interact. So you have a value here. So this is what we call a bad graph file, which is like a extended version of the original bad files. It would work, but the problem of that is the genome is so large. Imagine now for this different location, you might have 20 millions, 30 billions different coordinates. Originally, it's already a very large file, but now you are taking the square of the size, so you are making your bad graph extremely large. And actually, all these interactions are relatively sparse events. If you imagine such a big matrix, only a very small proportion of it would have interaction events. So whenever you are dealing with a data that is very large but very sparse, you probably want to consider some of the sparse matrix techniques. For example, here, if let's try to focus on this C001. So there are multiple different versions of sparse sparse coding. So we usually start from this C00, and that's the most easiest way. So instead of saving this entire matrix, now we save the first row and the third column. We have a wait, what is the example here? Yeah, so if you look at the first column here, so the first row, the second row, or the number one row, and the number one column would have a value of 2. So we just say 1, 1, 2. So the coordinates and the value is similar to the bad file. Okay, for the 0, for the 9 here is for 0 row and 2 column, we put the value 0, or we put the value 9, sorry, excuse me. So it will be this column, right? 0 to 9. So now, as you can see, in this way, we are only saving those values that are non-zero or that are not sparse. So if you are looking at a very sparse matrix, this way would compress your data size completely. Okay, and people have been developing similar linear algebra and similar algorithms for sparse matrix. For example, if you are transposing this original matrix, that is you would need to transpose everything in the memory. But using a sparse matrix, you can just change the row column, and you just swap the row column and column the row vector and the column vector, and you would get your sparse matrix transpose. That would be one example of why do we sometimes like to use this sparse coding. Now, this COO is the most classic coordinates, sparse coding way. But sometimes we want something more. Imagine most of our matrix manipulations, operations would be by each row or by each column instead of by each element. So sometimes if we save the values, the non-zero values from one row to be together, we might have a better efficiency to do some operation. So that's why the CSR is was invented. It's called compressed sparse column matrix. So now we look at each column, whether that's a column or a row, doesn't matter. So you just pick one slice, and you compress this slice, this vector first, and then you move on to the next slice. So in this way, even though the actual data size is the same as the C01, but for some of the algorithms, it can make a faster calling because it doesn't have to go through the entire linked list. Okay, so now this is the reason we want to have these cool files. So sometimes you will see, as you will see in the homework, that the .co files would be exactly using this format. Okay, in here you would have this .co is specifically designed by Cooler for genomic information. So you have, for each cool file, you would have actually four different data sheets. So the first sheet, the sheet 1, would be what are the chromosomes. For example, for a human, you have 24 chromosomes in total, 1 to 22 X and Y. And we have a separate file saving how do we define the bins. Yeah, so I forgot to talk about one thing. So if your matrix is too sparse, you can use this sparse compression to reduce your data size. And also because of the matrix is too large, and sometimes we don't need that high resolution, we can do the spinning like what we were doing before. We can truncate, not to try to truncate, we can summarize a very high dimensional vector into a lower dimensional space, but without losing too much information. So it's like a pooling or like a binning. Okay, so we now in this CoolFile, we have a separate file defining what are the bins. So would be, you know, where for each bin, where do we start, where do we end, and we just call that region to be, you know, region 1, for example, region A.1. That would be the label. Now the pixels are the data set we saw here. Okay, that will include the bin ID for the x-axis, the bin ID for the y-axis, and the value for that specific box. Okay, and the for the index one, I forgot what that means. Actually, I forgot. Okay, let's just leave it there. We wouldn't need this for now. So the most important part, as you can see, is the pixels data. That's the compressed version of the original large matrix. And to decode this back to the original matrix, you would need this binning information, this kind of metadata. Okay, so in practice, that's what we would have for the .co files. Now, for a lot of genomic interaction studies, you might need multiple resolutions. The resolution, by resolution here, we mean the size of the bin, the step size of the bin. Because you can imagine you can take, you know, 100,000 nucleotides as the bin, and then you have a lower resolution, but you can have a faster training, or you might have a better visualization. But for different tasks, you might need different resolutions. So this multi-resolution CoolFiles is a specific design for this. So you can save you know, multiple resolutions. It's like a folder of folders. It's like a folder of different CoolFiles. You can all save it in MCool. So these are the two, you know, typical file format for Hi-C and other genomic interaction modeling. Now let's move on to, you know, how to do this. Okay, so first of all, load your environment, load the cooler and everything, and now we provided you a CoolFile, and the let me see if I have it. 2.2 here. Yeah. So we provided you with this CoolFile. So now the first thing you need to do is to normalize it and to generate your multi-resolution cool file for the following up analysis. So the way we are going to do that is to save that, you know, the cool balance of the input file, and then to that will gives you a kind of rebalance or renormalized cool file, by which we mean that actually here, if you look at this data, sometimes this pixel data has not only 3 columns, but has a 4th column, or this binning metadata has a 4th column called weight. It gives you, you know, because different bins can have different lengths, and that is you know, some additional information your algorithm might want to take into consideration. So this balancing is trying to balance between different ways. And then you want to convert your Hi-C format from cool to a multi-resolution cool using this Hi-C convert format command. So it would generate automatically a series of different resolutions. If you want, you can specify which resolution you need, but you can also leave it as default, which gives you some 1,000, 5,000, 10,000, etc. Okay, so once we have that, we would move on to catch the Pikachu, catch the pig. But let me see, maybe now is a good time to take a break. Yeah, so I'll stop the recording now, so you can take a break, and just to trying to, you know, to rethink about why are we using this compressing information, and how are we saving this compressing information for genomic interaction data. Okay, I'll see you in a bit. Okay, so welcome back. Let's talk about this Pokemon Pikachu thing. Okay. So as we learned from Shirley's lecture, that if we have this Hi-SIN map, this contact map, we might be able to first to identify some obvious regions that are interacting much more frequently than each other. So like this triangle and this triangle. Okay, so we call these regions TAT, right? This is the regions. We can consider that to be the independent interacting unit here. But we are more interested in the thing that we are more interested in would be the unexpected interaction, the unexpected peaks in the blank region, in the blank area. For example, here we see there, we can tell directly, even as a human being, that there is some interesting peak happening here. For this one, we are not that sure. If we draw another box here, we are pretty confident there is no such thing. So this Pikachu is trying to say, now I want to train a computer vision model, image-based model, where we take each input like this, diamond region. We take the input like that, and then we're trying to make a machine learning model to, to classify whether this is supposed to be called as a positive peak or it's just a random noise. Okay, so that is the idea. So for this homework, we only need to use some of the pre-trained Pikachu models. And just give you a very brief introduction of this Pikachu, the methodology. It is taking, like I said, taking the input grids, taking the patches, and we manually provide them some labels, whether it's negative or that's a positive. So the positive labels are the things we directly get from input. So we know originally already which part can be positively interacting. For the negative samples, we just randomly sample some of the regions on the huge map, because the reason we do not specify where do we want is because we want to cover most of the features on the other part of the graph, and also we want to try to make the negative samples more diverse, but also try to avoid touching any false negatives. So this way, we basically just define positive cases, and then we random sample a few negative cases, and then you can train a binary classifier. This classifier can be neural network based, can be random forest. I believe this time we are using a random forest classifier. It can also use this as VM, a lot of other things. Doesn't matter. It's just a question we are trying to solve, trying to answer here, is to take a patch and trying to assign each patch a label, whether that is a peak or not a peak. And during training, you would still need to do cross-validation and parameter tuning, like we talked about in the first homework, or at least the first session, about how to do well machine learning. Okay, so that's the methodology, the concepts. And in terms of how to run Hi-C, how to run Pikachu, is that after you load this environment, there will be a command called Pikachu becomes available in from your terminal directly. So now you want to say, I want to use Pikachu to score for a chromosome, a specific chromosome, or I want to score for a specific genome. So it has these two options. Here we are more interested in this, specifically interested in this 21st chromosome. So we would use this score chromosome and try different resolution, different width of the binning, different whether do we use balance or not, what are the CRU data we are using, and what is the model we are using. So this CTCF model is a pre-trained classifier that we loaded from another kind of repository. So we also provided you this model in the P3 data. Try look into that and try to load this model directly for Pikachu. So this line would use this model, use this classifier to give a score for each of the region, for each of the bin region, a score for each chromosome or for each genome, to provide them a score for whether this is likely to be a positive or negative. And then we can now go into this output folder, and then you do this Pikachu again, because now you would have a very high resolution thing, and you do not want that high resolution, so you can do a pooling from this chromosome, from this first step, first stage outcome to get the ultimate outcome we want. Okay, so we will save it as a BADP. I would call it BADP file. So as you can see, for all these hyperparameters are something we can tune during model generation and also during model application. So here for the homework, we can just set the resolution to be somewhere between 1,000 to 10,000 would be enough for both visualization and also for classification. Okay, so that will gives you the peaks and the file of the peaks. Now we also ask you to do some visualization of the results, and to do that, HiGlass is one very powerful tool to directly use it. So I know you have already run some Python thing, but I'm not sure whether you have used Jupyter Notebook. So for this HiGlass, first of all, it has to be an interactive session. So it would require you to use Jupyter Notebook. And because you want to do this interactively, it is a little bit hard to do this with Canon. It's not impossible. You need to do a few port projections so that you can directly see the interactive kind of UI website that you can put in the Python code as just like what you put in your RStudio. So for this question, I would highly recommend you to download the result files. Make sure you only download the required files. For example, here we only need this ImCool file, which is what we generated from part 2.1, I think, the multi-resolution cool file. We only need this file, and to run everything here in the local Python. The reason of that is, as I said, so that the Jupyter Notebook can be easily, attached, and you can directly see your output. If you have any question regarding how to set up the Python environment, how to install this Jupyter, try to go back to the first session on how are we supposed to use Python. But for now, you can just try to start from install this Jupyter together with this HiGlass in Python. If you see this installation successfully finished, you are good to go. You are good to calculate directly to open a Jupyter Notebook and then to load your HiGlass over there. If not, go back to the previous slides, to previous labs. Okay. So now after you install this Jupyter, you need these 2 additional lines to link the HiGlass together with Jupyter. For now you don't have to know what these 2 lines are doing. It's just linking the HiGlass graphic interaction, interactive UI with Jupyter. And now after you successfully set up everything, you can just type in Jupyter Notebook. Let me show you what that means. Okay. I am showing you the entire window, right? I hope I am. Well, let me double check because I don't have an audience now. New share, just to make sure I'm sharing you the entire screen. Okay, hopefully nothing changed, but just in case. So in order to do that, we need to let me close everything here. Okay. So as you can see now, I'm at my home folder. Okay, it's not Canon anymore. It's my personal laptop. And the thing we are going to do is to, create a Conda environment that we have already created before, right? But now this time we want to activate some of the previously installed Python 3 environment. For example, here I'm going to use, this environment. I just rename it as Conda 3.8. Because here I would have a Python 3.8. So this is just my way to keep track of environments. But now I'm in this environment. Now I can directly go into Python, right? I can import whatever I need, right? I can import, for example, HiGlass. That should also work. I can do actually everything I want to do, but I just would not be able to see the graph, the figures, because of the nature of this terminal interaction UI. Okay, so in order to have all this graphic interaction, we would need to call this Jupyter. So we just give you a sense of how do we install it. So you just copy paste these 3 lines here. Okay, you install it. As you can see, it's all satisfied, and because I already installed it, but when you do it, it would take some time because you need to, as you can see, to load all of them to your local machine. It wouldn't be a very large space size, but it would take some time to install. And to run these 2 lines, to link Jupyter with HiGlass, you will see an OK if the linking is successful. Now, if you have everything settled down yet already, you'll be able to call Jupyter Notebook, and it would automatically generate a server. It automatically generates a server and give you saying now this Jupyter kernel is running behind in the backend, and now you can access this Jupyter by using, for example, this link, or it's actually automatically generate a link for you. So if you try it, you will be able to see. But for now, let me just copy this line with the link together with the token. Okay, so just imagine I don't have it. Right, I can just copy paste, and now I have this Jupyter. Okay, and now you want to navigate to your data folder, to your result folder, and create a new Python 3 notebook. I already created one. Yeah, the connection is failed because the original kernel was killed. I was trying to demonstrate this. Okay, so now the first thing we want to do is to import all the functions we need from HiGlass. Okay, HiGlass is a very nicely maintained package. The only function you need are the HiGlass itself. So you just you just load this HiGlass information, and now the second step is to load the data set. Oh, sorry, it's not connected, so I probably need to restart the kernel. Okay, so now let me load the HiGlass. So this is loading the environment, and now I'm loading the data set. Okay, so the HiGlass called this a track set, because if you go to the website, as we will do in a second, they call each data set to be a track set. They call each type of figure a tracker. Okay, it's not a very catchy naming, but that's how they do it. So now you have this TS1, which is looking at this cool file. And now you will define your own tracker. Here we are going to track a heat map of that set. Oh, sorry, not track set, the tile set. I should have probably changed tile set. So that is your data input as a TS1, and you track it. And now you want to view the plots, and you want to display it in a server. So you can just use all the functions built in, from HiGlass, and you just run it. So now it's already ready. Okay. And now you want to just call this display, and it gives you a interactive window with hopefully a heat map. Exactly. See. And now the fancy part of this is that you can directly drag this window. It can change to whatever shape you want. You have some buttons here that some of them do not work because they borrow this UI from their web portal. So some of the things you would not be able to use, but some of them they are. For example, you can add a figure at the top of this heat map or at the bottom of this heat map. And for this heat map, you can also change. You can also change. For example, the color. I forgot where the color is. Here, so you can change the color to different settings. You can generate a figure as you wish. So for the homework, this is what we need. But now let's go to the HiGlass portal just to see what they are providing us. Okay, so this is HiGlass, and we can look at some of the examples. For example, the example could be this one. Let's say just pick a random one. So HiGlass would allow you to generate multiple figures. For example, here it's probably using different resolutions. As you can see on the right, you have a higher granularity. Lower granularity, and on the right, on the left, you have a kind of a lower resolution. And then you will be able to change, the color for each of these. Let me try to do one. Hopefully it would work. It's not working. Maybe this background color doesn't mean what I suppose is meaning. Let's try to change a color code. This is something we can change. Okay, so this portal is providing you the way to generate multiple figures. So for example, here we are looking at 4 heat maps, but we can actually change. We can remove this heat map, I think. Close out series. Yeah, so now we have this tile again. So this is a data set. So this 4 might be 4 different data sets. But for this particular data set, we can now create a new, a new figure by looking at all these publicly available data sets. I just randomly pick one. And then we would have the heat map for that one. So we can generate, whatever we need on this portal. It's very fast. It's using the server to give you the calculation. The only shortcoming is that they do not support all the customized data set. It only has a given set of given collection of data sets that you can play around with. Okay. This time we are doing our own example, so that's why we have to do this locally. But just want to give you a sense of why you have these special buttons everywhere instead of just a heat map. So for this one, for example, originally, sorry, I already closed it. For example, in this one, let me just show you. I can actually, download the file. I can just export the files as a PNG or as a, a vector graph. This would work on the website, but for our own Jupyter, it might be harder. I haven't been able to do that, so you can please feel free to check it out. If you find out how to do it, let us know, let the class know how to do it. Because if you just download it here, it will just download you a empty figure. I really do not know why. So just for this homework, you can just make a screenshot of the heat map. That's all we want to see, so that we know that you learn how to use HiGlass to visualize a cool file or AMP file, and you also understand what a cool file is. Okay, so that is part 2.2. Yes. So now let's move on to the next question, part 2.3. The point 2 and point 3 and point 4 are very similar to each other. Not very similar, but are using the same data, which is the BAT-P data. Okay, BAT-P data. So we are again going to use this BAT tool because this time we are trying to find the interactions between between 2 different files. For this question 2.3, now we want to see those ATAC peaks, and we want to see the interaction of these ATAC peaks with the loops we identified from Pikachu. So this Pikachu is giving you the peaks, and it's also giving you the x and y of the peak, right? That's how you define a location in this two-dimensional matrix. So this x and y is called anchor 1 and anchor 2. So here in this anchor location file, this is the results we generated, right? Remember, we would have the interaction in a extended graph version, where you have x and you have y, and then you have the interaction score that is calculated by Pikachu. So now we want to say for these regions, and how many of these events would overlap with the peaks we identified using other techniques, using the ATAC sequencing techniques. Okay, so ideally we would see some association, but let's try try it on our own. So again, even though now this time we are not looking at the gene expression levels, we are looking at a score that we develop from other softwares. We are still trying to look at intersections between different genomic regions. So again, we have a reference file for a value for different region, and we have another file saying these are the regions of interest. So the function, the command, the software we are going to use is BAT tools again. So here, what we are going to do is very similarly, the bad tools intersect, but now just try to put the peaks as the first file and trying to put the anchor as the second file. So again, this is now becomes the peak. It now becomes the reference, the background reference, and now the anchor becomes the locations of interest. So you can calculate that, and you would be able to generate your data set. But just one thing to take into consideration. Now this bad P data is not like the bad data that bad tools would like to see, because it has X and have Y. And here we are actually interested in both anchors. Okay, interested in this anchor 1 and also in this anchor 2. So the way we are going to do is to take the first three columns, which would give you all the locations for all the anchor 1. And we would take the other 3 columns here, would gives you all the locations for all the anchor 2. And then we want to concatenate anchor 1 and anchor 2 together. We do not want to separately to analyze them, although we can. But here we are just concatenating them, and then we're trying to calculate directly this anchor, like in general anchor locations. I'm trying to look at the intersections between the anchor locations to the peaks background. Okay. Just one quick note on how to pick columns from Bash. We are using this AWK command, and using this specific syntax, it would gives you, the first 3 columns of the file of interest of your text file. And again, just to recap, this greater symbol means you are writing your output into a file. So if you want to calculate, now this will give you only the first 3 columns, which means the left anchor. If you want to calculate the right anchors, you just pick from the 4th to the 6th columns and save it in another file. And later on, you catch the anchor 1 and anchor 2 together, put the greater symbol. That gives you a concatenated version of all the anchors. And now you have all you need. You have the peak background file, you have the anchor file for the locations, and you are good to run these bad tools. Okay. And now we just apply these bad tools. As I told you, for 2.3 and 2.4, they are very similar to each other. For 2.3, you are using this ATAC peaks as the background. For 2.4, we are actually more familiar. We are going to use a gene expression specifically for chromosome 21 to generate what we done for what is the question, part 1. Part 1.2. Yeah, so for these figures, we are going to generate a very similar figure, trying to compare the anchor regions versus the overall general background regions to see if they have different levels. To see if they have any difference in gene expression levels. Okay. One additional thing for part 2.3 specifically is it want to identify not only the intersections, but also if there's any motifs for these intersections. To detect those motifs, we are going to use this find motif genome. And this is something we installed from a software called Homer. So for this question specifically, we want you to load another conda environment because they have some version conflicts. So remember to, like I said in the beginning, remember to use this one for part 2.7 only, for 2.3 only. Sorry, I was saying Mandarin number 3. And then if you come moving on to part 2.4 and other parts of the homework, go back to the same conda environment. Try to keep that in mind. Okay. And then after everything is successfully finished, you would see your result files under motifs folder. And then you can just generate, you can just download all of them. You will see results for different chromosomes, for different motifs, different regions, and you will also see a summary web page. Try to look into this web page, make some screenshots, and explain what you see from that results. Okay. So that will be our part for, that'll be all for the part 2. And now the only thing left is the part 3. And I think now is a good time to stop recording. Let me see if there's anything I want to keep in mind. Give me a second. Let me check my note. Yeah, I'm repeating myself, just trying to remember to switch between different locations. That's all you need to know. Oh, another thing I forgot to mention is that for when we talk about this sparse matrix in 2.1, we are saying, now if the matrix is very sparse, it's a good idea to save the information in a sparse format. Why don't we always do that? It's because apparently if you have a lot of values, instead of 5%, boxes has values, then imagine you have 90% of these are non-zero values, and you save the same matrix in this way. It's not that efficient anymore. It's not that efficient anymore. So you probably do not want that. And so you need to be clever on looking at your data. Some of the data is very sparse. You want to use this, some of them not. For example, here, if you look at this figure, even though you see here are mostly almost blank, you still have some values, right? So you imagine if you put this thing into a sparse format, that would actually increase the resource you need to do further calculations. So you probably one very frequent thing people do is to do some clipping. We just filter out all these small values and we set them. We just force them to be zero, so that when you do sparse compressing, it wouldn't wouldn't take too much space for those information. Okay, this is just one thing I forgot to say. Okay, so that's all I have for part 2. And let's take a break and let's move on to the final part. Okay, so now let's talk about the last part of our lab, the hidden Markov model and the TAD boundary identification. Okay, so we briefly talk about this HMM model in the lecture. That it's a statistical machine learning tool trying to help us identify hidden states from observation, from unobserved information through probability. Okay, so just a very quick recap, like what the hidden Markov model would be. Now imagine we just take the simplest example, coin flipping. Okay, I have a coin, I flip it for 100 times. I flip it for 10 times, let's say. And in 8 out of these 10 times, I got the head instead of a tail. It's not that unlikely, right? But we still feel, it might be something wrong. So now it's more like from the probability perspective, how confident we are to call this coin to be a biased coin, to be a unstable, unfair coin. So we learned that from our statistic classes that we can use this Bayes rule to calculate the conditional probability. Now, what the Markov model is trying to solve, what the kind of question Markov model is trying to solve, is that now, imagine we don't have a very stable coin, as in the coin is either fair or unfair. This fairness is also becomes a random random event. Imagine now we have this coin. It has 50% probability to be fair and 50% probability to be unfair. But now, if the coin is in the fair mode, then for the next event, for the next flip, the coin would be more likely to be a fair coin. Okay, so if you look at the diagram on the right, it's like if the coin is in a fair mode right now, next time it has 80% to stay in the fair mode. Similarly, if the coin is in the bias mode, next time it has 80% probability to stay in the bias mode. Now for a fair coin, you would have 50% each for heads or tail. But for a biased coin, you have a strong a preference over the tails than heads. So again, for this kind of system, we can define such a system. And the thing we can only observe would be the heads or tails. Now we have a sequence of heads or tails, say 100 flipping samples. We have a sequence of them, different patterns and different percentage. Now this time, how confident we are to say this coin is stable or unstable, or to say what is the probability behind, the different hidden states. Okay, so this is what kind of hidden Markov model is trying to solve. The reason it's called, hidden Markov model. First of all, because one, the state is hidden. We don't observe directly the states. And two, the system is Markovian. Markovian's, just a very quick recap, means, the probability of one event only depends on the previous event happening right before it. So that is, you only depends on the last minute, and your last minute only depends on the second last minute. So that is what we call a Markovian. So here in this state, this time, when we flip a coin, when we are imagining this hidden state, we know now this time, I flip it now for this particular point, for this at this particular time, I have a fair coin. So next time when I flip it, like the state of the hidden state of that coin would only depends on the hidden state right before this event. I wouldn't care that much about what's happening before 5 minutes ago, because I only look at the last hidden state. From our biological question perspective, why this is interesting? Because now imagine we are looking at a chromosome. Okay, we're using all this Hi-C, all these fancy techniques. We observe a lot of genomic interactions events. Now we know that if two regions are closer to each other, it is more likely to get a cross-link event. But we also know that due to the randomness, the stochasticity of the cellular system of the nucleus, is also fairly likely to get a cross-link just from a random interaction. Now the data we get from Hi-C would be a sequence of events, a sequence of interactions. We know that some of the interactions are because they are spatially closer to each other. Some of them they are not. But we also know that if we see a cluster of interactions, right? If we have a specific region of the chromosome of the genome where we see a lot of interactions, within that region, then we know they are probably interacting with each other, or spatially co-localizing to each other. So this is where the hidden Markov model can really help, because we do not know whether these regions are interacting or not, actually, because we just do not have this ground truth, and we would never have this ground truth, because the only observation we can make would be whether do we have this interaction event or not, instead of whether we are spatially closer to each other or not. Okay, so with this all set up, we can say, we can use all this, developed hidden Markov model that has been published out there. You have multiple different versions everywhere else. We will use the one we talk about during lecture, and also in the homework we also attach the link to the template of the code, to the algorithm. Okay, so now we imagine we have this system that has two states, up or down. Okay, we just artificially define it. We say the initial state for this system. So first of all, in total, we only have two states, two hidden states. But imagine now we have 8 observation states. Let's come back to this 8 later on. Let's just continue on this hidden Markov thing. Now, I say initially I have a 50-50% probability to be in either state A or state B. Okay. From the transition probability between state A and state B would be 90% or 10 versus 10%. So we have 90% probability to stay for one state, stay in one state, and we have 10% probability to flip sides. And we can also define a emission probability, like we talk about, like the observation probability. Now imagine we are in the state 1. What would be the probability of the observations we get? How frequent that would be? Or if we in state B, I'm in more immune mode, and I do not see a lot of interactions. But still, we have a probability distribution of how many events I would observe. Okay, so with all this setup, this now becomes a hidden Markov system, and we have a data, and then we can try to use the data to fit this model to see if this model is correct or not. Or the other way around, we can define this system first, and then we can make a sample. We can make a we can draw a sample. We can draw a sequence of samples, a sequence of events, based on our definition of the system. Now you may wonder, where are we getting this 8? So let's go back to this slide. So now the data we get from Hi-C is a continuous. You can consider that as a continuous observation, because the interaction can be 0, it can be 1, can be 10,000, can be 1 million. Even though theoretically speaking, they are still discrete. But if you imagine each single observation, each single value to be a separate state, then your system becomes too large. There's no realistic data set can be used to solve this problem. So now, as a compromise, we're trying to do the binning like we did in the previous questions. We're trying to bin those continuous distribution into different separate regions. And in R, we are using this function called cut. Okay, imagine we have this just in case some of you haven't used this card before. Imagine you have this X, you can generate this random uniform array where you generate from 0 to 1, you draw 100 samples. And now you can use this function cut to say, I want to cut this into 10 different bins. So it would generate a categorical array saying which class would your sample belong to. So instead of a continuous scalar value, now you have a categoric label of which region, which bin region you belong to. Similarly, just like similar to the histogram, you can also define directly the thresholds for the binning. You can define the number of bins you need, or you can instead you can define the coordinates for different bins. Now, so we load the data. We load the data, and it's something like let me see if I have a figure here. Give me 1 second. No. Sorry, where's my R? No. Okay, you cannot see it anymore. Let me share. Let me share the full screen. Okay, so imagine this is the data we have. Okay, we have this data. We provided you the data from the homework. Here I'm just using this data, so try not to copy the results. Just try to develop your own version. Now, if I load the data, and let's now look into the data, what the data looks like. So similarly, we have the region, the genomic region. So chromosome first, and then start point, end point. And we have this value, it's called DI, it's a direction index. In regarding to how do we define this DI, you can refer to the link we also attached in the homework. But just imagine this is something we want to predict, or we want to bin on. Okay, so this is kind of the data where for each bin here we have a value. For each bin here we have a value. So now imagine if we calculate just a middle point, like a midpoint between end point and start point. So just trying to merge, these two columns to sorry, I cannot click it anymore. It's the Zoom is hiding everything. Okay, so now imagine I'm just trying to merge the column 2 and column 3 to one column, so that's easier for the following up questions. Because as you can see, the bin size is relatively small. comparing to the actual value of the region. So it's only 40,000 comparing to 5 million. So we can just ignore the difference. But we just call this to be the label of this class. And now we take this middle point and we calculate it. And now we plot the data. The x is the midpoint. Sorry, the y is the midpoint, and the x is the DI score. Well, actually, that's incorrect. So x is the midpoint, and the y is the DI score. Okay, so now imagine actually now what we are looking at is a chromosome, right? It's a chromosome where for different regions you have a different DI score. As you can see, you have some ups and downs. It seems not that random because you see some clusters. For example, here you have this specific region where you have much more frequent ups than downs. Similarly, also here you have a lot of downs than ups. So our job here is trying to train a model that can separate this data into the two hidden states. You might argue, I just draw a line here from just at the y equals to 0, and all the points above 0 would be, I would call it an up, or all the values below 0, I would call this a down. So the artifact of that, the pitfall would be you are ignoring the stochasticity of the system. So you might end up with a lot of false positives. And also, you are undercutting your power because you already know with your prior knowledge that a cluster of events would means more information. So if you just draw a line here, you are basically making each prediction for each dot to be an independent prediction. So you are underpowering your data. So that is kind of the rationale why we are using this hidden Markov model. So in the end, what we want to have is, something like, do I have the figure? I do not. Let me try to run it. So just very quickly to get you, a sense of what we are trying to predict. Okay. So this is what we want to do, right? It's the same figure from this one, but now this time we assign a color for downs or ups. As you can see, for those clusters, for those big clusters, we would be able to, manually pick it. But for some of the small ones, for example, here, if you can see it clearly, some of the events, they are actually, even though they are, above the x-axis, we are still calling it to be a down state or to be an up state. That is, what the hidden Markov model can give us. Okay, so go back to our slides. So we are defining our system in this way, and we are using the code from you can use the code either from our lecture, or it's easier maybe to use the template from this link. We also attach it in the homework. So what this looks like is, this is what the block we put it there, and you can just go down for the here I'll talking about the examples and the theories behind the hidden Markov model. So you are all recommended to read through it. And they have two versions. They have a Python version. They also have R version script. So it's fairly easy. You just adapt this function and trying to put in your different inputs. So here what is your transition matrix? What is your emission matrix? What is your initial probability distribution? Okay, so with all this, you should be able to directly calculate a figure like what we are having like here in the slides. And trying to just do a manual check, just do a sanity check after you train the hidden Markov model to see if their prediction is reasonable. So if you see a mosaic prediction here, even though for some of the regions you can directly tell that should belong to one state, but instead the model is giving you an unreasonable prediction. Try to debug the code or try to change your training parameters, for example, number of iterations, etc. Okay, so that will be our homework 3, and that I would actually conclude our lab, because of part 4 is more about just question and answers. There will be no, it's more like conceptual. There's no coding not that heavy coding required for part 4. So we wouldn't cover that too much in the lab. But still, you're more than welcome if you have any unclear point you want us to clarify. But we wouldn't help you to solve this to answer those questions. Okay. So I just a conclusion. I know this 2 weeks can be quite overwhelming, because some of the problems that we are developing are actually, this year is actually our first year to trying to do this Hi-C and something related to this chromatin genomics. So if you feel sometimes it's a little bit lost, a little bit confusing, you are not alone. Okay, you're not alone. So please feel free to reach out to us if you find anything unclear, and try to stick onto this lab slides, trying to stick onto the instructions step by step, so that you can with the how to say, it's more optimistic, to stay on the good track, right? It's more hopeful to stay on the good track. Okay, so with that, I will stop the recording now, and I'll see you guys on Thursday, Friday, and Saturday. All right, see you later.